Hello there, and welcome back to the Science Sleepy Minds. Outside your window, the stars hang like lazy fireflies, frozen in their ancient twinkles. You lie back and imagine tracing a finger from one to the next, only to realise the truth. Even the closest of those suns would take you tens of thousands of years to reach with today's best spacecraft. It's a cruel joke, really. The cosmos is a playground built with no door handles, unless space itself has a hidden back door, because tonight we're folding the map. Picture this. Instead of crossing the vast desert of space inch by inch, what if you simply pinched two distant locations together and stepped through? No rocket fuel, no decades lost, just a neat little tunnel through the universe, like slipping behind a curtain and emerging on the other side of reality. Sounds lovely, right? Also completely impossible. Probably. Maybe. You probably won't survive this, at least not with current physics. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know your location and local time in the comments. I love seeing where you're all listening from. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float mentally into the unseeable architecture of the cosmos. Not stars, not galaxies, but the invisible scaffolding beneath it all. Because when we talk about wormholes, what we're really talking about is space itself, not as an empty void, but as a pliable, mutable thing. Einstein's great insight was that space and time weren't passive but flexible, stretchable, bendable, tearable. Well, let's not go full horror movie just yet. You're surrounded by this stuff even now. Space-time. It's the fabric you live on. Every step you take, every orbit your planet makes, it all unfolds across this great cosmic sheet. And just like a real fabric, it can wrinkle, it can sag. With enough mass, it can be pulled taut or shoved into curves so tight, light itself bends. And in theory, if space-time can be curved enough, it might even fold. Wormholes are not some modern Marvel movie quirk. The idea has haunted physicists since 1916, barely a year after Einstein unveiled general relativity. That's when Ludwig Flamm, fun name, right, noticed something odd in the math. A kind of mirror solution that hinted at a tunnel between two places. No one took it seriously. Not yet. Not until Einstein himself returned to the idea decades later. And what did he do? He teamed up with Nathan Rosen and scribbled out what's now called the Einstein-Rosen bridge, the first formal description of a wormhole. In theory, it linked two black holes, or possibly two distant regions of space-time via a tunnel. Sounds great, except it collapses instantly. Not great. See, wormholes are heartbreakers. The moment you try to use one, it evaporates. The walls slam shut. You're left alone in the dark with your classical physics textbooks and a crushing sense of disappointment. And yet, no one can quite prove they're impossible. That's the maddening beauty of it. Wormholes live in the grey zone between what's mathematically permissible and what's physically plausible. They're not science fiction. They're science with an asterisk. They sit right on the border, like a quantum raccoon with a foot in each trash can. Historians still argue whether Einstein meant for the bridge to be traversable, or was simply playing with math, unaware that future generations would try to crawl through it in theory. You float there, picturing space not as a flat grid but as something more tactile, like a stretch of rubber or maybe soft pizza dough. And yes, it's 2 a.m. You're definitely hungry now. You imagine poking two fingers through the dough, pushing them together until they touch from opposite ends. That's the wormhole idea. 2 mouths, 1 tunnel, 0 travel time. If you survive the tidal forces and you're okay with a few pesky violations of the known laws of physics. Which you might be. Let's be clear, no wormhole has ever been detected. No probe has zipped through one. No alien has stepped out from a glittering blue portal to share their galactic hummus recipes. And yet wormholes remain deeply seductive to physicists, especially the ones who can't sleep and start scribbling impossible things on chalkboards at 2 in the morning. Just like you, lying there, half dozing and half drifting through your own private universe of what-ifs. Why do we care about wormholes so much? Maybe because they offer the one thing space refuses to give us, a shortcut. The cosmos is vast but deeply frustrating. Our best probes crawl like snails across a beach that spans trillions of miles. Wormholes mock all that. They offer the promise of elsewhere, now, and in a way that's the most human fantasy of all. To leap across boundaries, to cheat time, to skip the hard journey and just arrive. One fringe idea, you'll like this, is that wormholes might already exist in nature, but be microscopic. Tiny pinpricks in the foam of space-time popping open and close trillions of times per second. You wouldn't even notice. Unless, of course, one decides to stabilize, which it won't. Probably. But still. Sleep tight. You might wonder, why don't we just try to make one? Dig up some wormhole dirt, build one in a lab? Oh, we'll get there. But be warned, this is not your average IKEA project. You can't just slap together a few black holes and expect the universe to roll with it. Still, you should feel proud. You're venturing into one of the most mind-stretching corners of modern physics. A place where travel doesn't mean movement, where distance is a suggestion, and where your morning commute could, in theory, involve a casual stroll through a space-time tunnel. Assuming you survive the negative energy fields, collapsing walls, and spontaneous temporal paradoxes. Oh, and the math? It's horrifying. We'll take a peek at it soon. But for now, just enjoy the image. Two mouths of a tunnel, yawning open across the galaxy. A traveller steps through and vanishes. And on the other side, somewhere else, maybe in a different time altogether, they emerge. You stand on a fabric you can't see. Beneath your feet, around your fingers, even within your lungs as you breathe, space isn't empty, and it's certainly not passive. You've always moved through it without noticing, like a fish that doesn't know it's in water. But space, according to Einstein's nervous system melting insight, isn't just where things happen, it's what things happen on. You've probably heard the phrase spacetime, maybe thrown around in some documentary narrated by a velvet-voiced astrophysicist. But let's be clear, this is the stage, the set, and the script of the universe, all wrapped into one massive four-dimensional construct. 3 spatial dimensions plus one of time, twisted together like some kind of cosmic licorice. Sounds tasty, isn't? Einstein didn't invent gravity. What he did was ruin it, in the best possible way. Before Einstein, gravity was just Newton's polite force. Planets tugged on each other, apples plunked off trees with a sense of respectable decorum. But Einstein came along and said, actually, mass bends space-time. Things fall not because they're pulled, but because the floor curves beneath them. Imagine rolling a marble across a trampoline. You're not pulling the marble, the sheet does the work. Now take that trampoline, expand it into 4 dimensions, throw in a few black holes, some high-velocity cosmic spaghetti, and boom, you're in the realm of general relativity. Space-time isn't uniform either. It warps, it shifts, it stretches when galaxies swirl into existence. It dimples when you sit on your couch. Yes, technically, you're creating a tiny gravitational field by binge-watching your favourite show. And when enough mass piles into one spot, it can fold the fabric into such extreme angles that, well, things get interesting. And here's the bit where wormholes start to shimmer in the math. The idea isn't just space is bendy. The truly bonkers part is that space and time are inseparable. Moving through one affects how you experience the other. Clocks tick slower in gravity wells. Rulers shrink when things move fast enough. And with the right arrangement, something impossibly dense, or something that involves hypothetical exotic physics, you might just fold the fabric. That's what a wormhole would be. Not a hole in the traditional sense, like you dig in your backyard and worry about sprinkler lines. It's more like a tunnel between distant points, through space-time itself. A short path between 2 faraway locations, or moments. Or, in some of the wilder models, dimensions. Historians still argue whether the term wormhole was first used in physics as a metaphor or a literal descriptor. The image came from an apple. Picture a worm chewing from one side of the fruit to the other, making a tunnel through. The worm ignores the surface, skips the long journey and arrives instantly. Smug little bugger. You pause and imagine it. Space as an apple, stars scattered across its skin, and then that secret, forbidden passage curling quietly through its heart. That's the dream, the cheat code, the whisper in the equations. But that metaphor only works if you can imagine this thing, space-time, as material. That's the key mental twist. You're not just a traveller in space, you're a creature of space-time. Every second of your life is a movement through this fabric, not just across your kitchen floor or down the street, but forward in time as well. You're always in motion, always falling through the fourth dimension. And sometimes, as the equations say, you could take a detour. Weirdly enough, this isn't pure fantasy. Mathematically, space-time doesn't forbid the idea of a shortcut. In the right conditions, with the right amount of warping, twisting, and maybe a sprinkling of negative energy, a tunnel connecting distant points could form. The problem? Those conditions are ludicrous. You'd need something that bends space-time not just inward, like a black hole, but in on itself in a kind of inside-out loop. The geometry becomes non-Euclidean. Light can circle endlessly, and time may do the same. Some models look less like a tunnel and more like a cosmic grommet pinched into the universe's quilt. Let's drop a historical gem here. In the 1930s, a lesser-known physicist named W.J. van Stockham published a paper on rotating cylinders of infinite length and infinite density. Why? Because he suspected that spinning might twist space-time into closed loops, like twisting a towel. If you did it right, you might create a loop that circled not just in space, but in time. Early ingredients of wormhole theory? Arguably yes. Utter madness? Also yes. Fringe idea alert. Some theorists wonder if spinning black holes, or even cosmic strings, thin filaments of hypothetical early universe matter, might have twisted space-time into pre-existing wormholes. You'd never know, of course, unless you happened to stumble into one, or unless one opened under your pillow and you found your cat aging in reverse, in which case, please call literally every physicist immediately. You're probably wondering, is any of this testable? And the answer is, not easily. Detecting the shape of space-time is like trying to spot the architecture of fog, but we do see its effects. Gravity lensing, where light bends around a massive object, shows us how space curves. GPS satellites have to correct for time dilation, because Earth's gravity warps time slightly compared to orbit. These aren't fun theories, they're real-world adjustments. Without them, your phone couldn't find your pizza place. Still, a full wormhole? That's orders of magnitude beyond anything we've measured. It's one thing to note that light bends, it's another to suggest it could vanish into a hole and reappear across the galaxy. Yet the equations don't scream no. They whisper maybe. Physicists like Kip Thorne, yes, the one who consulted on Interstellar, have worked out actual models, mathematically valid, of traversable wormholes. The catch: they require exotic matter to stay open, and we haven't quite stumbled over a stash of that in your neighbour's garage. We'll get into that later. You'll love it. It breaks about a dozen physical assumptions and probably some moral ones too. In the meantime, you keep floating through the fog of space-time, through the delicious mystery of a universe that keeps offering questions with no clear answers. And somewhere out there, or maybe folded nearby in a direction your brain can't picture, a shortcut might exist, or might have, or will. And as you sink deeper into that thought, remember, the path to a wormhole doesn't just stretch across space. It curls around the edges of your imagination. You're floating now, comfortably suspended in the strange warmth of possibility. The stars feel closer, as if they're waiting just outside your reach. But you know better. Even the nearest one is a brutal 4.3 light-years away, which is cosmic slang for nope. You would have to travel for tens of thousands of years in your current form just to say hello, unless you cheat. And that's where wormholes drift into view, not as fiction, but as shimmering hypotheticals backed by the unyielding logic of Einstein's general relativity. They go by many names: Einstein-Rosen bridges, Lorentzian wormholes, spacetime tunnels. But their promise is the same: space itself could let you skip the boring middle bits. So, what exactly is a wormhole? At its simplest, it's a tunnel connecting 2 points in space-time. Not just a line drawn on a map, but a shortcut through the map's very fabric. Imagine taking a piece of paper, drawing 2 dots on opposite corners, and folding the sheet until they touch. The distance between them is now 0. That crease, that's the wormhole. The visual is clean. The reality is gloriously messy. To even define a wormhole properly, you have to abandon your usual notions of direction, distance, and durability. Because here's the first uncomfortable truth. Most wormholes, if they exist at all, don't stay open long enough for even a photon to pass through. They snap shut instantly, like the universe second-guessing its own physics. That's because space-time doesn't like to be bent without a reason. It resists. It sags back into place like a stubborn mattress. But that hasn't stopped physicists from poking the idea with increasingly fancy sticks. The original blueprint came in 1935, when Einstein and his colleague Nathan Rosen sketched out a solution to Einstein's own field equations. They weren't trying to invent teleportation. They were trying to unify particles with geometry. What they found was something that looked suspiciously like a tunnel, a kind of bridge between 2 regions. You wouldn't want to drive through it, though. The entrance is a black hole, and the exit, well, it doesn't stick around. That's the key flaw with the Einstein-Rosen bridge. It's not traversable. The tunnel pinches off faster than any signal can make it through. Think of it like a trapdoor that collapses into itself the moment you peek in. Useful for theoretical modelling, terrible for space tourism. Historians still argue whether Einstein and Rosen even realise what they had drawn. Some believe they thought of it as a purely mathematical curiosity, a quirk of the equations, not a real-world pathway. Others suggest Einstein may have secretly suspected more, but left it for future minds to unravel, which, to be fair, is very on brand for him. But the idea wouldn't die. It mutated, grew teeth, and started showing up in serious discussions about the geometry of space-time. Here's where things get spicy. Not all wormholes are born equal. Some theoretical models describe Euclidean wormholes, which don't exist in real time, but rather in imaginary time. A concept from quantum field theory that is equal parts genius and gibberish. These aren't tunnels you could fly through, more like ghostly shadows in the math, hints perhaps of deeper truths. Then there are Lorentzian wormholes, named for the Lorentz transformations that govern relativity. These are the kind of wormholes you might actually use, at least on paper. They have structure, they have entrances and exits, and most importantly, they might be kept open, if you have the right kind of matter. More on that soon. But first, let's detour into a charming little wormhole known as the Morris-Thorne model. In 1988, Kip Thorne and his graduate student Mike Morris decided to answer a very specific, very wholesome question. Could a wormhole be made safe for humans to travel through? Why? Because Carl Sagan had asked. No, really? While writing Contact, Sagan wanted to make sure the travel method for his protagonist was scientifically plausible. He phoned a friend, Kip Thorne, and suddenly the field of traversable wormhole physics got a real kick in the pants. The result was a model that included all the necessary ingredients: a stable tunnel, no event horizons, and a throat wide enough for a spacecraft to pass through without being instantly obliterated. Neat. The catch? The tunnel has to be held open by exotic matter, stuff with negative energy density, which in normal person terms is matter that doesn't just defy gravity, it repels it. Don't bother checking your pantry. Negative energy isn't something you can scoop into a bucket. It exists in theory, and in the margins of quantum experiments, like the Casimir effect, where two metal plates in a vacuum experience a mysterious pull, possibly due to quantum fluctuations. But turning that into a wormhole support structure, that's like finding out matches work and then trying to ignite a star. Still, it's not ruled out, and in physics, not ruled out is sometimes the best we can hope for. Fringe theorists have speculated wildly about how wormholes could exist in our universe without violating known physics. One idea involves naturally occurring wormholes from the early universe. Primordial shortcuts formed when space-time was still stretching itself into place. Another suggests that black holes might contain hidden wormholes at their cores, waiting to be discovered like secret tunnels in a cosmic prison. Of course, this would require surviving a black hole's event horizon, which is about as survivable as trying to backstroke through a meat grinder made of math. Yet the dream persists, because wormholes offer more than just fast travel. They hint at something deeper, the malleability of reality, the idea that the universe may not be as stubbornly linear and vast as it appears, that under certain conditions, with enough knowledge, energy, and perhaps some cosmic mischief, space itself might let us skip ahead. And who wouldn't want that? The true weirdness lies not just in their potential, but in the fact that the laws of physics whisper that they could be real. There's no giant neon sign saying forbidden, just a quiet set of rules with tiny exceptions, little windows of maybe. You lean into that thought now, as if the fabric of the universe might soften under your weight. You imagine two mouths, maybe on opposite ends of the galaxy, maybe in different centuries, connected by a tunnel outside Time's Arrow, invisible, impossible, and maybe, just maybe, waiting. You're drifting now through thought and theory, winding deeper into this strange underground of space-time where tunnels might bloom like secret root systems beneath the stars. And if the idea of a wormhole still feels too surreal to believe, well, blame Einstein and Rosen. They gave the cosmos its first official fold. It's 1935. Albert Einstein, still rocking the wild hair and deep frown of someone trying to wrestle the universe into submission, is working with physicist Nathan Rosen. Together, they're wrestling with a cosmic contradiction. You see, black holes had already crept into the math, and they didn't make Einstein comfortable, not one bit. Black holes, those dense monstrosities where gravity gets so intense even light can't escape, weren't officially proven yet. But they were lurking in the equations like something sharp in the dark. Einstein didn't like the idea of singularities, places where math goes full diva and throws up its hands. He wanted the universe to behave. So he and Rosen sat down with the field equations of general relativity and tried to iron out the wrinkles. They came up with something unexpected, a model that connected two separate sheets of space-time through a sort of bridge. On paper, it looked smooth, a symmetrical, neat solution that tied two regions together without singularities, without the chaos of infinite density. They weren't trying to build a shortcut, mind you. They were trying to model particles as geometric structures. But what they found was a mathematical throat between two universes. Later, physicists called it the Einstein-Rosen bridge. You know it by a more poetic name, a wormhole. Now, before you pack your bags, there's a catch, and it's a pretty big one. Their solution was elegant, but useless. The bridge collapses faster than a Jenga tower in a toddler's birthday party. The moment anything tries to travel through, the walls cave in. It's like building a subway tunnel out of smoke and hoping no one notices. Still, the idea lingered. Like a song you can't stop humming, the Einstein-Rosen bridge haunted the physics community. Could this thing be made stable? Could a bridge actually be held open? Historians still argue whether Einstein truly believed the bridge was a traversable wormhole or just a tidy mathematical trick. Some say he dismissed it as purely theoretical. Others point out that he often planted seeds and left others to water them. What we do know is that the idea caught fire decades later. Enter John Wheeler, a physics legend, and one of the rare humans who could say, "I coined the term black hole," and actually be serious about it. In the 1950s and 60s, Wheeler began exploring the chaotic geometry of space-time, and he coined the term wormhole to describe these bizarre tunnel-like structures that seem to pop up in the equations. Wheeler's work was fringe, radical, and kind of beautiful. He proposed that space-time at the tinier scales might be frothing with activity, little bubbles and tunnels constantly forming and vanishing in something he called quantum foam. These wouldn't be giant portals you could fly through, more like Planck-scale hiccups in reality, the cosmic equivalent of static. And then there was the moment someone asked, what if some of these tunnels didn't collapse? What if, just maybe, one of them grew? Of course, growing a wormhole from quantum foam is like trying to inflate a soap bubble until it becomes a hot air balloon. You're going to need some pretty serious tools, and we're not even close. But in theory, if you could somehow stabilize the throat, that tunnel might stay open. And that's when the real fun begins. But again, the Einstein-Rosen bridge, that one's no good for travel. It connects two Schwarzschild black holes, basically non-rotating, non-charged black holes, through a hypersurface. But anything entering that tunnel would be crushed before it got anywhere. It's like building a bridge with no supports, across an earthquake, during a hurricane, out of dreams. Now let's get weird. Some later interpretations took the Einstein-Rosen bridge and said, hey, what if this isn't a bridge across space, but a bridge between universes? Yes, the multiverse idea gets sprinkled in early. If each mouth of the bridge opens into a separate universe, then wormholes aren't shortcuts within our world. They're doorways to others. There's no experimental evidence for this, of course, but the math just loves to keep the options open. One fringe idea, that the universe began with wormholes. Some of them stretched out in the Big Bang, others collapsed, and a few survived. Maybe tucked into dark corners of space-time where no light reaches. Maybe lurking in the hearts of black holes safely hidden behind horizons. And here's a particularly fun paradox. Some physicists wondered if the other side of a black hole is a white hole, a hypothetical object that spits matter out instead of sucking it in. The Einstein-Rosen bridge would connect the two, but the travel would be one way. You fall in a black hole, emerge through a white hole, somewhere or somewhen. Trouble is, white holes may not exist, or they may exist only in the equations, cosmic anti-objects that laugh in the face of entropy, which makes them basically mythical beasts, like unicorns made of math and regret. Still, you have to admire the dedication, because what started as a shaky attempt to dodge the singularity problem ended up opening a rabbit hole into the very bones of reality. One humble bridge collapsing under its own weight sparked decades of speculation, rewrites, quantum loopholes, and heated arguments over chalkboards. And let's be honest, it's just plain cool. There's something deeply satisfying about the idea that space could contain secret passageways, that the universe might come with back doors, shortcuts, Easter eggs hidden in the geometry itself, like a cosmic cheat code waiting to be discovered by the right kind of stubborn. So here you are, floating in the legacy of two brilliant minds who dared to ask, what if these equations go somewhere? The first wormhole wasn't practical, but it was a seed, and it's still growing. You drift beside the ghost of a tunnel, nothing more than math scribbled across blackboards and curled into the minds of physicists pulling too many all-nighters. You've stared down the Einstein-Rosen bridge, admired its symmetry, and watched it collapse in your imagination like a house made of fog. But now comes the real problem. Let's say you want to actually use a wormhole, not just theorize about it, not just dream about cosmic shortcuts while sipping lukewarm coffee at 3 a.m. You want to step through. You want to enter one end, wave a breezy goodbye, and emerge somewhere else before your tea even cools. Here's the issue. Wormholes, by default, do not want to be helpful. In fact, they behave like panicked, overdramatic actors on a stage. They collapse the moment you try to do anything useful. And the universe, always the pessimist, insists on reminding you that any tunnel through space-time is inherently unstable. Why? Gravity. The same force that gives you weight, keeps your drink on the table, and glues moons to planets. is the same force that tries to slam a wormhole shut the moment it opens. It's as if space-time itself flinches. You have to imagine the geometry like a throat, a tunnel pinched between two flared openings. This throat is where things get delicate. The second mass or radiation tries to move through it. Even something as innocent as a single photon, it contributes to the stress energy of the structure. The fabric folds in on itself. The throat collapses. Tunnel gone. Thanks for playing. This was proven formally by multiple studies, including a cheerful little theorem from the 1970s that basically says, sorry, wormholes aren't naturally traversable. The equations are unforgiving. If you don't actively hold the tunnel open, it shuts quickly. So the question becomes, what could possibly hold it open? What scaffolding could prop up this throat against the crushing weight of its own geometry? You're going to need something that pushes back, not just ordinary matter, not even neutron star matter. No, you need something exotic. The theoretical kind of substance that doesn't just ignore gravity, it mocks it. But before we dive into exotic matter, don't worry, we will, it's worth understanding just how hostile wormholes are by default. It's not just gravity trying to ruin the party. The very curvature of space-time gets violent near the throat. The tidal forces, as physicists call them, stretch and compress anything that gets close. Think of the spaghettification that happens near a black hole, those famous gravity gradients that turn objects into cosmic noodles. A similar fate could await anything approaching a wormhole throat that's not properly stabilized. Historians still argue whether early theorists truly understood the violence of this environment. Some of them sketched wormholes as neat, gentle tunnels, quietly glowing like something from a utopian future. But the truth is far more chaotic. These things would be unstable, twitchy, and eager to shut themselves the moment your spacecraft politely knocks at the entrance. Fringe idea alert. A few theorists have toyed with the concept of naturally stable wormholes, ancient relics from the early universe, kept open not by exotic matter, but by unusual topological quirks. Essentially, the universe might have rolled its space-time dice just right, creating a few permanent tunnels between distant regions. If those exist, they're hiding extremely well. A few physicists have run simulations of what such an object would do to its surroundings. Light would bend in strange ways. Stars behind the tunnel would appear in duplicate or stretch into rings. In some cases, gravitational lensing would reveal distortions that could be interpreted as a wormhole signature. So far, no dice. But telescopes like the James Webb are finally looking with enough precision that if one was nearby, we might spot it. But until then, the task remains. If we want a wormhole we can actually use, we must engineer it, and that means resisting the forces trying to snap it shut. Cue the theoretical scaffolding. You might try putting negative pressure at the throat, something that acts like tension instead of compression. Unlike a bridge held up by stone pillars, you'd be holding space-time open with anti-gravity struts. And while that sounds like something invented by a 12-year-old designing their dream spaceship, it's shockingly consistent with what the math says is needed. What we're dancing around is the null energy condition, one of those deeply mathematical laws that says, loosely, matter and energy shouldn't behave in impossible ways. But if you break that law, if you introduce something that violates the null energy condition, then suddenly, wormholes become stable, traversable, and deeply suspicious. Here's the kicker. The equations don't forbid that. They don't prefer it, but they leave the door open. And so, theoretical physicists go hunting for loopholes, for matter that doesn't behave, for energy that isn't just negative in a mathy way, but negative in a physical, space-time bending sense. Something that says to gravity, no thanks, I'm going the other way. But for now, you're just standing here, facing the mouth of a wormhole that cannot yet stay open. It trembles, it pinches, it collapses, like a secret you're not yet meant to hear, and it's waiting for the right physics, for the right pressure, for a traveller bold or bored enough to try something impossible. Because while the tunnel may slam shut today, The future is wide open, so let's get weird. You're standing at the edge of a cosmic throat trying to pry it open like the world's most stubborn drawbridge. You've already learned that regular matter won't cut it. Even the densest stars can't hold the tunnel. Gravity just squishes it shut like a vacuum-sealed bag. So what now? What could keep a wormhole propped open long enough for you to tiptoe through it? Enter exotic matter. The unicorn of physics, the ghost pepper of theoretical constructs, the stuff that shouldn't exist but mathematically kind of does. Now don't confuse exotic with unusual. This isn't just matter with a weird haircut or atoms that listen to jazz. Exotic matter is something entirely different. It possesses negative energy density, which means if you placed it in a gravitational field, it would push rather than pull. Let that sink in. We're talking about stuff that, when dropped, would fall up. And as ridiculous as that sounds, it's not just sci-fi gibberish. It actually appears in the equations of general relativity and quantum field theory, but in strange, narrow circumstances. Take the Casimir effect, for example. It's one of the few real-world demonstrations of negative energy, and it's deeply spooky. You place two uncharged metal plates extremely close together in a vacuum, nothing between them, and yet they attract. Why? Because of quantum fluctuations, the endless jittering of virtual particles in empty space. The region between the plates ends up with less energy than the surrounding vacuum. Boom! Negative energy. Just a little. Just enough to jiggle the plates. But still, it's like discovering anti-gravity in your toaster. Fringe theorists love this stuff. They take the Casimir effect and start daydreaming about scaling it up, adding more plates, trapping more quantum fluctuations, eventually stockpiling enough negative energy to punch open a wormhole. This is where physics becomes equal parts math and mischief. Historians still argue whether exotic matter violates fundamental energy conditions, like the weak energy condition, which essentially says energy density should never be negative for any observer. But in the world of quantum fields, rules like that start to blur. Under very specific conditions, the laws allow tiny localized violations, like little legal loopholes in the contract of the universe. Of course, there's a massive catch as exotic matter is not the same as antimatter. Don't mix them up. Antimatter annihilates regular matter when the two meet, releasing energy. But exotic matter is not about opposites, it's about inversion. It warps space in the opposite direction, and you'd need a lot of it. Calculations suggest that to hold open a traversable wormhole big enough for a person, or worse, a spaceship, you'd need an amount of exotic matter with negative energy equal in magnitude to the mass of an entire star. Not exactly something you can order on Amazon Prime. Even the Casimir effect only produces this negative energy at quantum scales, so small you'd need a microscope and a miracle just to detect it. Still, it's not impossible, not prohibited. The physics doesn't scream no, it just sighs and says, "Okay, but good luck." So how would it work? Imagine a tunnel between 2 points in space, curved and pressurized by this negative energy scaffold. The exotic matter lines the throat like an invisible support beam, countering the inward crush of gravity. It doesn't just keep the tunnel open, it makes the geometry stable. You could, in theory, pass through without becoming cosmic linguine. That's why it's so exciting. If exotic matter exists, or could be manufactured, it would make traversable wormholes more than just a beautiful equation. It would make them physically real. Here's a quirk you'll love. Some models suggest that a wormhole throat lined with exotic matter might repel anything with mass, like two magnets refusing to touch. That means you'd have to approach carefully. No crashing through the mouth like Han Solo, more like tiptoeing into a region of intense space-time weirdness, while your ship's sensors scream, "Why are we doing this?" But of course no one's found exotic matter yet. Not in usable amounts, not in labs, not in nature. It remains for now a theoretical requirement, a placeholder in our equations. The scaffolding we wish we had. The whispered what-if that keeps wormholes on the edge of plausibility. Still, there's a whole zoo of strange constructs out there. Negative energy density. tachyonic fields, hypothetical particles that always move faster than light and might stabilize exotic structures. Phantom energy, a form of dark energy with pressure so negative it could rip the universe apart and possibly keep a wormhole open along the way. No one knows if these things are real. Some physicists say we might one day generate exotic matter through high-energy particle collisions, like in the Large Hadron Collider. Others think it might show up naturally in the early universe, or in some unseen corner of black hole interiors. And then, of course, there are the wildcards who suggest alien civilizations, way more advanced than us, might have already figured it out. Don't laugh. There's a fringe theory that the absence of exotic matter in our part of the cosmos might be the result of intergalactic cleanup, as in, someone used up all the negative energy keeping their own wormholes open, as if they borrowed the keys and left us with a locked door. But until we can find or create this bizarre form of matter, wormholes remain in a frustrating limbo. They're possible if we can violate certain energy conditions, if we can stabilize negative energy, if we can wrap our heads around quantum gravity, if we're okay bending the rules just slightly without snapping the whole universe in half. And still, despite the cosmic wish list, you can't quite shake the feeling. The universe might be hiding this stuff from us, like it's playing a game, daring us to come closer. Because if exotic matter does exist, truly, fully, it wouldn't just let us open wormholes. It would change everything. You could build a tunnel between worlds. You sit back now, letting your mind stretch like the fabric of spacetime itself, trying to wrap itself around a delicious little loophole. What if wormholes could make you go faster than light, without actually breaking the speed limit? Let's be clear, Einstein's laws are pretty adamant about this. Nothing with mass can travel faster than light in a vacuum. Not your spaceship, not your dreams, not even the screaming regret you'd feel mid-wormhole if it turned out to be a dead end. Light is the ultimate cosmic speed cop, and it's got citations ready for anyone who tries to cheat. But wormholes? They're a different beast. You're not speeding through space, and you're taking a shortcut around it. It's the old folded paper trick again. Picture two stars on opposite ends of a napkin. To travel between them the regular way, you'd have to go across the fabric. But if you fold the napkin so the stars overlap and punch a hole through, that's a wormhole. Now your journey is instant, at least from an outside perspective. And here's the kicker. You never technically exceed the speed of light locally. You move through the tunnel at a perfectly reasonable pace. It's space itself that cheats. The distance inside the wormhole is far shorter than the distance outside it. This is what physicists call a topological shortcut. Space doesn't have to be Euclidean or flat. It can bend, fold, twist and connect, back on itself like a pretzel designed by M.C. Escher on a caffeine binge. From the perspective of someone watching from outside, say, sipping tea on Earth as your ship disappears into a wormhole and pops out 100 light years away, it looks like you just travelled faster than light. You didn't. You just used a better route. Historians still argue whether faster-than-light travel via wormholes violates causality, that is, the cause and effect order of events. Some say it does, others say it's fine, as long as you don't make a U-turn. Spoiler, we'll talk about time travel very soon. But for now, just enjoy the mind-bending idea that wormholes could, in principle, allow you to reach stars, galaxies, even other corners of the observable universe in a matter of minutes, or seconds, without ever breaking the rules of relativity. This isn't theoretical fluff either. In 1988, that same Kip Thorne and Mike Morris duo who brought you the human-safe wormhole also explored this very concept. They realised that if you placed one mouth of a wormhole near Earth and the other light years away, and you could stabilise it, you could make the ultimate interstellar highway. Fringe idea time. Some physicists have suggested that wormholes might connect not just distant locations in space, but places separated by enormous gulfs in time. You could, in theory, use a wormhole to skip the centuries it would normally take to get from Earth to, say, Andromeda. Of course, there's that tiny nagging issue, building or discovering such a wormhole in the first place. Let's say, just for fun, that advanced aliens did it, because naturally, they could leave behind a network of wormholes scattered across the galaxy. You wouldn't need to travel at light speed, you just need the interstellar version of Google Maps. Tap the right coordinates, step through, and voila, you're orbiting a gas giant on the other side of the Milky Way. There's even a hypothesis in the deep end of theoretical physics that dark matter halos might be shaped by collapsed or hidden wormhole entrances. If true, we might be inside a wormhole right now without knowing it. The math doesn't rule it out. Still, let's imagine a practical scenario. You have a spaceship. You have a wormhole mouth parked in orbit above Earth. The other end is placed somewhere near Alpha Centauri, roughly 4.3 light-years away. You enter, coast gently through the tunnel, and emerge at your destination in seconds. Now, to someone on Earth, you appear to have arrived faster than light could have travelled the distance. Did you break physics? Nope. You just ignored the space between. And here's where things get fun and uncomfortable. If you move one end of the wormhole at high speed, say via a relativistic ship, and then bring it back, time inside the wormhole may no longer match time outside. Now you've created a time offset, which means, oh yes, you guessed it, you've built a time machine. We'll circle back to that paradox-laden can of worms soon, but for now, let's admire this strange little workaround. Wormholes don't let you go faster than light through space. They make the space itself shorter. Imagine a mountain range. To cross it, you hike up and over, long, hard, exhausting. But someone comes along and builds a tunnel through the mountain. You're still walking at the same speed, but your trip is now 10 times faster. The mountain didn't change, you just bent the terrain. A wormhole is a tunnel through the mountain range of space-time, and you? You're the hiker with suspiciously advanced quantum boots. Let's toss in a slightly unsettling fringe concept for good measure: self-sustaining wormholes. Some physicists suggest that a wormhole, once stabilized, might be used to generate its own exotic matter, like a loop. The energy feedback from the tunnel's geometry could theoretically reinforce the structure, keeping it open indefinitely, as long as it doesn't collapse, explode, or spiral into a paradox, which it almost certainly would. But maybe not before you got a postcard home. And don't forget, wormholes aren't the only theoretical way to go faster than light. You've got the Alcubierre warp drive too, which shrinks space in front of you and expands it behind. Same idea. Cheat distance. Don't touch the light speed limit. But wormholes remain the romantic favourite. They're mysterious. They're cinematic. They're the promise of an elsewhere without the pain of the journey. And if someone, some civilization, some future version of us, ever learns to stabilize one, then light speed will no longer be the ceiling. It will just be the floor. So there you are, tunneling across the cosmos in your nice negative energy-lined wormhole, minding your own business, gliding through space-time like a smug interstellar subway passenger. Maybe you just zipped from Earth to Alpha Centauri in under a minute. Maybe you've stopped checking the laws of physics because, frankly, they've been more like loose suggestions lately. But then, you notice the clocks aren't in sync. Time's off. And not just a little. You check your watch, glance at the control panel, squint at a nearby chronometer, and realize something has gone terribly sideways. Because if wormholes can connect distant points in space, and you move one of those points fast enough, you might just create a bridge between two different moments in time. Congratulations, you've made a time machine. Now go ahead and panic. This isn't just a wacky sci-fi twist, this is baked right into the logic of relativity. Time and space are deeply linked. So when you start manipulating one, the other wiggles along like an annoyed twin sibling. And wormholes? They're the ultimate space-time wiggle. Let's run a simple scenario. Suppose you've got a wormhole with two mouths, mouth A and mouth B. Initially, both are synchronized. You step through either end and pop out instantly on the other side. Great, but now you take mouth B on a relativistic road trip. Put it in a spaceship, accelerate it close to light speed, then bring it back to its original location. Thanks to time dilation, less time passes for mouth B than for mouth A. Maybe only a few hours pass for the one you moved, while years tick by for the one you left behind. And because the two mouths are still connected via a tunnel through space-time, you've now created a loop where someone could step in through B and exit in the past at A. Wormhole arrow spaceship, arrow clock skew arrow paradox. Historians still argue whether Thorne and his colleagues were fully aware of the time travel implications when they published their wormhole papers in the late 80s. Some say they were focused on the geometry. Others believe the causality headaches came later, like the worst kind of theoretical hangover. Either way, it didn't take long for people to notice the implications. And oh boy, the implications. You've now built a scenario where effects could precede causes, where a person could exit the wormhole and do something that prevents their own entry. The classic grandfather paradox rears its temporal head. What happens if you go back in time and stop yourself from building the wormhole in the first place? Physics does not enjoy this question. Some interpretations of quantum mechanics allow for multiple timelines. In that view, you simply hop to a parallel version of the universe where the paradox resolves itself. But others say no, that space-time must be consistent, and that any attempt to change the past would somehow be thwarted. Maybe the wormhole collapses. Maybe the universe hits a cosmic nope button. Maybe you get distracted and forget to commit the paradox-inducing act. Time, after all, is stubborn. Fringe idea time. There's something called the chronology protection conjecture, proposed by Stephen Hawking. His suggestion: the universe doesn't allow time machines. As soon as you try to create one, quantum effects, like vacuum fluctuations, pile up catastrophically, closing the wormhole before anything paradoxical can occur, like space-time setting off a fire alarm. It's a theory, not a proven law, but it's elegant. Hawking basically said, nature abhors a time loop. Still, if you could prevent those quantum effects or shield against them somehow, you might get a working wormhole time machine, maybe even a very limited one, only usable between the 2 points after the wormhole's creation. No ancient Rome visits, no dinosaur selfies. But you could, in theory, send information or travellers a few hours, days, or even years into the past, within the wormhole's operational window. And that opens up, well, problems. Military-grade problems, political problems, causality erasing, reality glitching, headache-inducing what-if problems. Because if wormholes are time machines, then the very act of knowing about them might trigger a paradox. Imagine receiving a message from the future telling you not to build the wormhole you're currently constructing. What do? Obey? Ignore it? Wonder if your inbox is haunted? Fringe theorists have explored using wormholes for closed time-like curves, paths through space-time that loop back on themselves. If you throw an object into the curve, it returns to the same space-time coordinates again and again. A looping rock, a whisper caught in an infinite echo. One famous thought experiment involves a billiard ball fired into a wormhole. It emerges in the past, collides with its past self, and knocks itself off course, preventing itself from entering the wormhole in the first place. Cue the logical implosion. Yet in some simulations, there are solutions where consistency prevails. The ball hits itself just right, adjusting its trajectory in a way that still allows the loop to occur. A kind of self-consistent paradox. The universe, it seems, can be flexible, as long as the loop closes cleanly. And here's the wildest bit. There's no consensus. Some physicists say wormholes can't be time machines because the quantum instability near their mouths would explode into infinite energy. Others say, sure, why not? And then spend 30 pages describing the geometry of a time-looping spaceship. The laws of physics don't give us a clear answer, they give us math. And that math, depending on the assumptions you make, either whispers maybe or screams absolutely not. But if wormholes can exist, and if exotic matter can hold them open, and if you can accelerate one mouth and create a time offset, then the possibility is real. You could send a message to yourself. You could see yourself arriving before you left. You could, in theory, witness your own future. And that's where things stop being theoretical. Because even if we never build one, even if wormhole time machines are forever trapped in the realm of thought experiments and science fiction, they still teach us something powerful, that the fabric of reality is stranger than we ever imagined. That time is not a river, It's a landscape. And somewhere buried in the folds of that landscape, a tunnel might lead not just across the galaxy, but backward through the very idea of now. You're somewhere in the deep back corridors of spacetime now, wandering through the wormhole idea like a curious tourist with an interdimensional flashlight. You've seen how it might let you cheat distance. You've seen how it could let you cheat time. But to really appreciate how wormholes fit into the gravitational family tree, you need to take a step back and meet their weird, often dangerous relatives. Because wormholes are not lonely anomalies. They're part of a deeply dysfunctional, mostly theoretical family that includes black holes, white holes, and a few theoretical uncles we're not even sure exist. Let's start with the black hole. You know it, you love it, and it definitely doesn't love you back. A black hole is a region of space-time where gravity has gone full drama queen. Mass gets squeezed so tightly into one point, called a singularity, that the escape velocity becomes greater than the speed of light. Nothing gets out. Not light, not information, not your regrets. It has an event horizon, a kind of gravitational point of no return. Once you cross that, you're committed. It's like replying sure to a mysterious group text. You don't know what's coming, but you're in it now. The idea of black holes goes all the way back to the 18th century, when Jean Michel and Pierre-Simon Laplace imagined dark stars whose gravity was strong enough to trap light. But it wasn't until Einstein's general relativity came along that the math truly allowed them. And even then, Einstein himself didn't like the idea. His equations predicted them. He didn't believe nature would allow them. Spoiler, it did. Fast forward to today, and we've got loads of observational evidence, stars orbiting invisible points, gravitational waves from black hole collisions, even that hauntingly blurry image from the Event Horizon telescope, a cosmic donut of doom. But black holes are only half the story. Flip one around in time and you get a white hole. White holes are the theoretical inverse of black holes. Instead of sucking everything in, they spit everything out. Nothing can enter. Matter and energy are ejected, like a very tidy explosion. If black holes are cosmic drains, white holes are fountains. But there's one small hiccup. We've never seen one. In theory, a white hole could be the other side of a black hole, especially in a maximally extended solution of the Einstein equations like the Kruskal-Zikaras model. That's the sort of math that tries to be fair to all possible timelines. You've got your black hole singularity, and connected to it, a mirror image, a white hole, flinging matter into the universe like a cosmic sneeze. Historians still argue whether this was ever meant to describe real physics or just mathematical completeness. Some say the white hole exists only to balance the equations. Others suggest it might have existed in the early universe, when conditions were more exotic, chaotic, and willing to tolerate that sort of nonsense. But here's where things twist again. A wormhole, in its simplest theoretical form, can be thought of as a bridge between a black hole and a white hole. This is the so-called Einstein-Rosen bridge again, the one that snaps shut if you try to travel through it, but exists beautifully in theory. Matter falls into the black hole mouth, zips through the throat, faster than light could have moved through space, and emerges through the white hole mouth. Only it doesn't work for real travel because, well, you die. Details. Now let's get extra strange. There are theories where both ends of a wormhole could be black holes, or neither. In some speculative models, the mouths of a wormhole look just like regular regions of space until you get close. Only then do you realise the light bending, the gravitational lensing, the sense that geometry itself is cheating. You could mistake a wormhole mouth for a black hole until someone, or something, vanishes into it and reappears elsewhere. Fringe theorists have even proposed the existence of naked singularities, gravitational points of infinite density without the polite shroud of an event horizon. In classical general relativity, these aren't supposed to exist. They break predictability. They're like having a chaotic bug in your universe's source code. But if one did exist, it might behave like a one-way wormhole entrance, or exit, or something even worse. And let's not forget graver stars, boson stars, and other hypothetical objects that might look like black holes from the outside, but behave very differently inside. Some of these structures could, maybe, possibly, contain stable wormhole-like cores. They're the astrophysical equivalent of a haunted house that's actually an elevator to another city. So here's the growing realization. Wormholes, black holes, white holes, they're not separate ideas. They're all connected through the same gravitational mathematics. They're different solutions to the same underlying equations. Like alternate personalities in spacetime's wild, tangled psyche. Here's a visual trick you can try, if you're still awake and your brain isn't sizzling. Picture the universe not as a flat sheet, but as a warped terrain. Black holes are steep pits, almost infinitely deep. White holes are impossible hills. Wormholes? They're tunnels under the terrain, shortcuts carved into the landscape itself. And somewhere, in that terrain, there might be structures we haven't even imagined. Things that blur the line between gravitational object and geometric phenomenon. Maybe a black hole is a wormhole under certain quantum conditions. Maybe white holes are real but rare. Maybe the difference between them all is just a matter of frame, perspective, or a few exotic equations we haven't discovered yet. One thing's for sure, if wormholes are real, they're part of a messy gravitational family, riddled with paradoxes, heavy with energy, and prone to collapsing at the worst possible moment. Still, you can't help but wonder, what if the next black hole we study is more than just a pit? What if it's a door? You're drifting now, a seasoned wormhole tourist with a head full of collapsing tunnels, negative energy, and the unsettling realization that time might be more of a suggestion than a rule. But as the theoretical dust settles and the equations fade into the background hum of your sleepy mind, one thought rises to the surface like a friendly glowing sci-fi cliché. Haven't I seen this in a movie somewhere? Yes you have. Because wormholes, these physics-bending marvels that may or may not exist, have found a very cozy, wildly inaccurate home in popular culture. And it turns out, we humans really like using them to explain away long-distance travel, paradoxes, and the occasional intergalactic romance. Let's start with the obvious one, Interstellar. When Christopher Nolan's 2014 space epic hit theatres, audiences were introduced to a rotating black hole named Gargantua and, more importantly, a stable wormhole near Saturn. This was no throwaway sci-fi gag. Nolan brought in Kip Thorne, actual physicist and wormhole specialist, to consult and make sure the film's physics wasn't complete gibberish. And sure enough, Interstellar gave us one of the most visually accurate depictions of a wormhole. A sphere, not a flat portal. Why? Because from the outside, the mouth of a wormhole wouldn't look like a swirling disk. It would look like a sphere reflecting light from its other end. Like a cosmic marble. Or a soap bubble hiding another galaxy inside. It was beautiful. It was trippy. It was only slightly ruined by Matthew McConaughey whisper-crying through 5 dimensions. Of course, Nolan took some liberties. The wormhole was hand-placed by future humans, and the interior time-looping bookshelf room at the end. Let's just say Kip Thorne didn't sign off on that particular plot twist. Still, Interstellar did something rare. It treated wormholes as real physics, not magic, not wizard holes, but serious, dangerous scientific possibilities that came with consequences, and it blew millions of minds in the process. But Interstellar wasn't the first, or even the silliest. Let's rewind to Contact, another movie inspired by Carl Sagan's fascination with wormholes. In the film, Jodie Foster's character rides a kind of gravitational amusement park ride through space after a machine opens a tunnel using, you guessed it, a wormhole network. She travels to another star system in seconds, though no time seems to pass on Earth. It's neat. It's vague. It gave thousands of viewers whiplash. That one was also advised by Kip Thorne, by the way. This man is basically the wormhole whisperer of Hollywood. But pop culture has never been shy about abusing wormholes. Take Stargate, the long-running sci-fi franchise in which a ring-shaped device creates a wormhole between 2 planets. Step through one end and you're on another world, usually fighting bad guys or yelling in tactical vests. The physics? Let's just say the show's explanation of wormhole physics involved a lot of blinking lights and very few actual field equations. Or Star Trek, where wormholes are used so frequently they may as well be listed in the credits. The most famous, of course, is the Bajoran wormhole in Deep Space Nine, a stable tunnel connecting the alpha and gamma quadrants of the galaxy. Unlike most of the Star Trek universe's techno-babble, this one was surprisingly grounded in science fiction lore. The wormhole is spatially stable, has 2 fixed mouths, and can be travelled in both directions. Sort of. Unless the script says otherwise. Even Marvel gets in on the action. Doctor Strange and his fellow sorcerers casually sling portals open with hand gestures and sass, which, sure, looks amazing. But let's be honest, this is less wormhole physics and more cosmic uber. Still, these depictions, while often scientifically dicey, serve a deeper purpose. They tap into something primal, a longing, a dream. Because at its core, a wormhole isn't just a plot device, it's a metaphor, a physical expression of our desire to skip the waiting, to go farther, faster, to erase the tyranny of distance and reconnect with what's out of reach. Even the ancient myths flirted with the idea. Gods and heroes leaping from world to world, vanishing through gates in the sky. Stone circles, sacred doorways, stargates long before they had scripts and soundtracks. The idea that the universe might contain hidden paths is one we've carried for millennia, and today we dress it up in quantum equations and CGI. One fringe theory you'll love. Some researchers believe if an advanced civilization ever used wormholes to travel, the wake of that passage might leave behind faint distortions, trails in the fabric of space. So if we ever detect a gravitational anomaly that can't be explained by stars or dark matter, maybe we're just catching the tail end of someone else's shortcut. Of course, skeptics argue that if wormholes were ever usable, we'd probably already know. There'd be wormhole-based tourism, a best portals of the Orion Arm travel guide, reality TV shows called Through the Hole. You get the idea. But maybe it's not that simple. Maybe wormholes are unstable, dangerous, or maybe they require resources we haven't discovered, something buried deep in quantum gravity, or hidden within the fine structure of space-time itself. Maybe alien civilizations just learned to stop playing with causality before they accidentally erased their parents. Still, you can't help but smile at how deeply wormholes have burrowed into our collective imagination. They're in movies, books, video games, t-shirts, conspiracy theories, probably 1 or 2 questionable tattoos, and each time they carry the same secret promise. There's more, there's a way, there's a hidden path through the impossible. You may not have a wormhole in your garage yet, but you carry one in your mind, curled up like a question waiting to unfold, and the fact that we keep imagining them again and again might mean we're inching closer to the day we open one for real. So now your dreams are paved with starry tunnels and cinematic shortcuts, wormholes shimmering like cosmic cheat codes just waiting to be unlocked. But here's the thing. No one warns you about when you're busy binge-watching sci-fi or casually building hypothetical wormhole time machines in your head. What if wormholes aren't large? What if they're already here? Just really, really small? Welcome to the twitchy, particle-jittering realm of microscopic wormholes, a place where space-time isn't smooth and serene, but frothy, chaotic, and wildly uncooperative. A place where, according to some of the more daring branches of theoretical physics, wormholes might be popping in and out of existence all the time, under your bed, in your cereal bowl, right now in the air between your fingers. Don't worry, they're harmless. Probably. This all begins with something called quantum foam, a term coined by John Wheeler. Remember him from the weird gravitational family reunion? Wheeler suggested that at the Planck scale, we're talking 10 to the negative 35 meters, which is a trillionth of a meter, space-time itself becomes unstable, no longer a smooth, continuous fabric, more like a boiling, seething froth of uncertainty. Historians still argue whether Wheeler's quantum foam was a formal proposal or more of a poetic image to capture the wild energy of space-time at the smallest scales. Either way, it stuck, and the idea is simple. Zoom in far enough, and space-time stops behaving. It jitters, it loops, it creates virtual particles, it fluctuates, and in some models, it gives birth to baby wormholes. Imagine that. 1,000 tiny wormholes forming and collapsing every nanosecond, like soap bubbles in the vacuum. Each one a miniature tunnel, possibly linking different regions of space, or even different universes, for a fraction of a heartbeat before vanishing again. Of course, they're too small to detect, too unstable to travel through, too theoretical to make it into mainstream physics conferences without someone raising an eyebrow, but they're fascinating. Because if these tiny wormholes exist, they suggest something huge. The universe might be naturally inclined to connect distant points, over and over, all the time, on the tiniest scale possible. And here's where things get spicy. Some physicists have speculated that under the right conditions, one of these microscopic wormholes might stabilize. Maybe it latches onto a particle. Maybe it gets caught in a high-energy event. Maybe, cue dramatic music, it gets grown. This is sometimes called the wormhole enlargement hypothesis. Not an official title, but it should be. It suggests that a tiny wormhole, properly fed and engineered, could expand into a traversable size. Think of it like nurturing a bonsai tunnel into a fully grown space portal. It's wildly speculative, but the math doesn't rule it out. And since we don't yet have a full theory of quantum gravity, the elusive physics that would unite general relativity and quantum mechanics, we can't say for sure what spacetime is doing at the Planck scale. One fringe idea even connects these micro-wormholes to entanglement. That's right, the spooky action at a distance that made Einstein grumble. Some theorists, like those behind the ER equals EPR conjecture, suggest that an entangled pair of particles might be connected by a microscopic wormhole. The ER part stands for Einstein-Rosen, wormholes, and the EPR stands for Einstein-Podolsky-Rosen, entanglement. Coincidence? Maybe not. In that view, wormholes aren't just possible, they're everywhere. Hidden behind the scenes of particle physics, binding the quantum world together like cosmic superglue. But again, these aren't travel-sized. You're not crawling through an entangled electron anytime soon. Still, imagine what it would mean. If these wormholes exist in nature, even fleetingly, it suggests that space-time has a kind of built-in connectivity, a tendency to link distant places. And that means wormholes might not be alien technology or the result of super-advanced civilizations. They might be natural, ordinary, even common. We're just too big and clumsy to notice. Let's get even weirder, shall we? There are theoretical models where dark matter could be influenced, or even partly explained, by networks of microscopic wormholes. Imagine trillions of tiny tunnels influencing gravity ever so slightly, subtly distorting the distribution of matter in galaxies. We can't see them, we can't detect them directly, but their gravitational fingerprints might be everywhere. Fringe theorists have even proposed that these micro-wormholes could act like cosmic routers, transmitting information across vast regions of space at near instantaneous speeds. Not by sending particles, but by changing entanglement correlations. If this is true, the universe might already be a deeply entangled, wormhole-laced communications network. And here you are, still trying to get your Wi-Fi to reach the kitchen. Another deliciously speculative idea that our own brains might be laced with tiny wormholes. Yes, really. Some physicists and fringe neuroscientists, a terrifying combo, have played with the idea that consciousness, whatever it is, could be partially rooted in quantum effects. If so, maybe some form of micro-wormhole plays a role in thought, awareness, or memory. Is it testable? Not yet. Is it publishable? Only if you don't care about tenure. But it's fun to think about, that the universe might hide its greatest mysteries not just in black holes and nebulae, but in the subatomic fizz of our everyday lives. Of course, this all hinges on the big unknown, quantum gravity. Until we have a working theory that unifies general relativity, which governs big things, and quantum mechanics, which governs tiny things, we're flying blind in this territory. We can guess, simulate, write equations that behave nicely under idealized conditions, but we can't prove what spacetime does when it's that small. It's like trying to understand ocean currents by staring at a single drop of water, and so the microscopic wormhole remains a maybe, a footnote in the physics textbooks, a blinking placeholder in the simulation, a whisper behind every twitch of a particle. You'll never see one, you'll never crawl through one, but just maybe your atoms already have. You're lying there now, fully entangled with the idea that space might be humming with microscopic tunnels, popping open and slamming shut like invisible blinks of cosmic mischief. But at some point, the idle daydream becomes an itch. The theories, the movies, the maybe baby wormholes, all of it leads to one irresistible question. Can we build one? And not a subatomic wormhole lurking under your pillow, not a quantum flicker of connectivity between electrons. Number, a real, traversable wormhole, one you could walk through, drive through, send a rover through, maybe toss your annoying coworker into. So can we, please? Well, let's build a checklist, shall we? First you need space-time, got it. Then you need to bend it into a tunnel. Tricky, but Einstein's general relativity lets you do that, in theory. Then you need to keep it open, which means fighting against gravity's relentless urge to slam it shut. So, exotic matter? Check. In the hypothetical sense, anyway. Then you need stability. Because even a wormhole lined with exotic matter would be like balancing a bowling ball on a greased trampoline during an earthquake. Wormholes aren't just fragile, they're neurotic. A single photon of regular matter entering the throat could shift the energy balance just enough to cause a collapse. And by collapse, we don't mean a gentle closing. We mean catastrophic implosion, singularity formation, and possibly not being able to file a return trip claim. To prevent that, the wormhole needs constant maintenance, pressure, containment, fine-tuned energy balancing that makes juggling knives while skydiving look like a beginner's yoga class. Historians still argue whether the earliest proposals for traversable wormholes were even remotely practical. Some physicists, like Michael Visser in the 1990s, tried to map out realistic geometries with minimal exotic matter, but even those models still required engineering capabilities were about as close to as ants are to 3D printing hoverboards. But say we did crack exotic matter. Say we harvested negative energy from quantum vacuum states, built up a stash, and carefully arranged it into a pressure shell surrounding the wormhole throat. What next? You'd need a way to shape it, to keep the geometry stable in four-dimensional space-time. This means manipulating spacetime curvature itself, not with rockets or reactors, but with gravitational control far beyond anything we can do today. You're not just building a tunnel, you're editing the map of reality, and that means engineering on a Planckian level. Some fringe ideas suggest that extremely strong magnetic fields could help stabilize spacetime distortions. Others propose using rotating masses, like gigantic spinning rings of dense material, to mimic the conditions needed to stretch a wormhole throat. But in either case, we're talking megastructures here. Dyson sphere adjacent. Projects that would make the International Space Station look like IKEA furniture. And remember, this isn't just a spatial engineering problem, it's also temporal. Once you introduce time offsets between the mouths of a wormhole, by accelerating one for example, you open up potential causality violations. Even if the wormhole holds open, the universe might get angry. Quantum effects could destabilize it. Vacuum fluctuations could pile up. A tidal wave of radiation might surge through the tunnel and fry everything inside like a microwave set to vengeful God. Some models suggest you'd need a time-dependent metric to manage this. Basically, an adjustable spacetime equation that adapts to feedback inside the wormhole in real time. In other words, you'd need a wormhole autopilot AI that can calculate Einstein field equations on the fly, at Planckian precision, while you're inside the tunnel. Good luck debugging that software. But let's get optimistic for a moment. Suppose we overcome the engineering hurdles. We find exotic matter. We stabilize the geometry. We avoid quantum catastrophes. Now comes the practical stuff. Where do you build it? Earth orbit? Too much interference. Moon base? Maybe. Deep space? Likely best. How do you transport one mouth? If you want to create an interstellar bridge, one mouth has to be moved far away at sublight speeds. Unless, of course, you find a naturally occurring wormhole and just tape your infrastructure onto it like a giant cosmic GoPro. What keeps people alive inside it? The tidal forces inside a poorly engineered wormhole would tear a human, or even a well-armoured probe, to shreds. You'd need smooth curvature, low tidal gradients, and probably radiation shielding on par with sun-diving spacecraft. What happens if it destabilises mid-trip? Let's not even go there, but do pack an emergency singularity escape plan. Some researchers have suggested the first traversable wormholes, if they ever become real, might be data only. Small, stabilised tunnels for sending quantum information across vast distances. You wouldn't go through yourself, but your entangled particles could. Think quantum communication systems that skip light speed limitations. Still, the big dream remains: walkable wormholes, actual shortcuts, step in here, step out there kind of travel. And weirdly, despite the madness of it all, the physics doesn't strictly forbid it. Nothing in the known laws says you shall not build a wormhole. The equations allow it, carefully, begrudgingly, with 1,000 caveats and a strong implication that you'll probably blow yourself up trying. But not forbidden is the best thing you can hear in theoretical physics. It means someone, somewhere, might figure it out. And maybe, just maybe, they already have. Fringe idea time. What if wormholes have been built, but we can't detect them because their mouths are cloaked? Not by stealth fields, but by being so deeply curved into local space-time that they look ordinary from the outside. You'd pass them every day without knowing. A parked wormhole could be hiding behind the moon, or inside the sun, or worse, at the bottom of the Mariana Trench. And if someone ever does build one, let's just hope they leave good instructions, because folding the universe is one thing, but folding it neatly, that takes genius. You've made it this far, through foam and paradoxes, black holes and backdoors, quantum chaos and cinematic wormholes that look suspiciously like glowing cereal bowls. And now, here you are, sitting at the intersection of science, engineering, and classified dreams. Because if wormholes are theoretically possible, and if exotic matter might, just maybe, exist, then you know what comes next. Someone somewhere is trying to build one, or at least trying to work out if it's worth a line in a budget proposal. You pull up a seat and lean in. Welcome to the shadowy realm of government agencies, defense projects, and classified physics programs that don't quite admit what they're working on. But every now and then, a curious phrase pops up in a declassified report: non-locality, metric engineering, space-time modification, or the ever-enigmatic propulsion beyond conventional frameworks. Yeah, that kind of language. Let's start with the space nerds, NASA. Specifically, the folks over at NASA's former Breakthrough Propulsion Physics project, quietly launched in the late 1990s. Their goal? To explore propulsion technologies that didn't rely on chemical fuel or solar sails or waiting several centuries to reach another star. Wormholes were on the menu. They never promised to build one, but they did publish papers on whether the energy requirements for a wormhole could be made manageable. Spoiler, not yet. But that didn't stop them from poking at the math. Then came DARPA, the US Defense Advanced Research Projects Agency. You know them. They're the ones who helped give us the internet, stealth tech, and robot dogs that look like they escaped from a dystopian petting zoo. DARPA has dipped its toes in space-time before, most famously with the 100-year Starship Initiative, launched in partnership with NASA's Ames Research Center, to explore the long-term feasibility of interstellar travel. While wormholes weren't a primary focus, the language surrounding propulsion independence from conventional thrust left just enough wiggle room to keep theorists curious. Historians still argue whether DARPA has ever seriously funded wormhole research, or whether the topic is kept just vague enough to dance around public scrutiny. Officially, no known program admits to building or stabilizing wormholes, but unofficially, the rumours swirl. Fringe theorists have a field day with the idea that wormhole research might be buried in black budget programs, those classified projects with no public accountability and enough funding to try the impossible. After all, if a wormhole could provide instantaneous communication or strategic mobility, even just for signals, the military implications would be enormous. It doesn't have to be send a tank through space. Even just sending information faster than light across battlefields or satellites would rewrite the rules of global defense. And if that's not enough to raise eyebrows, consider this. In 2008, a US defense contractor submitted a patent involving spacetime modification weaponry and gravity wave manipulation. Yes, it was rejected. Yes, it was vague and suspiciously Star Trek-y. But still, it was filed. Someone typed that phrase. On government time. And don't forget the Russian side of things. Back in the Cold War, Soviet scientists dabbled in torsion field theory, a speculative framework that suggested spinning masses could warp space-time in strange ways. It never made it into accepted physics, but it hinted at a national appetite for weird. The kind of weird that sounds like wormhole precursors if you squint hard enough and ignore the mathematics. Even China has recently funded basic research into exotic propulsion systems, including negative mass dynamics and vacuum fluctuation engineering. Do those phrases mean wormhole directly? Not necessarily, but they're dancing in the same ballroom. Now let's get speculative. There's a persistent conspiracy-adjacent theory that a few advanced projects, not necessarily government-run, have already experimented with wormhole-like effects. Some point to strange anomalies in data from particle accelerators. Others, more dramatically, claim that unidentified aerial phenomena, the kind with the blinking lights and sudden direction changes, may operate via localized space-time warping. Now, look, we're not saying your neighbour's drone is a wormhole probe, but we're not saying it either. And if the tech isn't being secretly developed, then here's the bigger mystery: why not? Why isn't wormhole research a bigger priority? Well, probably because it's nearly impossible. Even the most generous models suggest energy requirements far beyond what we can produce. Even the most optimistic lab setups can't keep a particle-scale wormhole open for even a femtosecond. And even the best physicists working in theoretical labs are still searching for a framework that connects general relativity with quantum mechanics. Without a theory of quantum gravity, wormhole science is like trying to design skyscrapers before discovering concrete. And yet, the interest lingers, quietly, patiently. Because even if we're not building them now, someone eventually might. And maybe, just maybe, that's why certain files stay closed, why certain phrases stay vague, why certain patents get filed and then quietly forgotten. Fringe idea: what if wormholes can't be discovered casually? What if they require intent? Some researchers have suggested that wormhole access, especially for time-related versions, might require more than machinery. Perhaps a conscious observer must be involved. A specific interaction between mind and metric. Yes, this dips into fringe territory, but it's not entirely out of step with some interpretations of quantum mechanics. And even if it's not true, it's enough to keep some people up at night, staring at the ceiling, wondering if the reason we haven't found wormholes is because we're not asking the right questions. So here we are, on the edge of possibility. Physics says maybe, governments say classified, and the stars say nothing at all. They just wait, maybe watching, maybe listening, or maybe, just maybe, opening a door when we're finally ready. You're still here, still drifting in that heady blend of science and speculation, and now you've arrived at the cliff edge of the real challenge. The math, that's right. No more cinematic wormholes or secret lab daydreams. Tonight you're peeking behind the curtain at the equations themselves, the terrifying, beautiful structures that either keep wormholes alive or strangle them in the cradle. So grab your imaginary chalkboard, roll your neck, and prepare to dance with curved geometry so intense it might make your high school math teacher weep into their coffee. First, we need to talk about Einstein's field equations. Now don't run, this is the heart of it all. The Big EFE, as the cool theorists call it, is essentially a set of 10 interlinked equations that describe how matter and energy curve space-time. They're the reason planets orbit stars and why your feet stay on the ground instead of floating off toward Canada. In their terrifyingly elegant form, they look something like this. Gn plus Ln equals open parenthesis 8, pi g over c to the 4th power close parenthesis. Yes, that old chestnut. Here's what you need to know without your brain boiling. G mu nu describes how space-time is curved, the Einstein tensor. T mu nu describes the matter and energy in that space-time, the stress-energy tensor. The rest of it is just constants and background music from the universe. So what happens when you try to shove a wormhole into these equations? You don't just ask, can I punch a hole in space-time and walk through it? You have to build a geometry, a shape of space-time, that satisfies these equations. It has to be a solution, a shape that doesn't make the equations scream or the math spiral into infinite nonsense. This is where Morris Thorne wormholes come in again. These were designed in 1988 specifically to be traversable solutions to the field equations. They're spherically symmetric, meaning the throat of the wormhole is the same in every direction. A nice, clean circle, not a cosmic wind tunnel. The whole structure is engineered to minimize tidal forces and avoid event horizons, for passenger comfort. To do this, Morris and Thorne used what's called a static metric, meaning the wormhole doesn't change over time, at least not until you mess with it. Their chosen metric involves a shape function and a redshift function, terms that define how the tunnel curves and how much gravity distorts time inside it. The fun part? To keep this wormhole open, the equations require T mu nu to include negative energy density. You remember that from before? That's your exotic matter, the thing the universe hates but might secretly allow in dark corners. What this means is, the geometry demands weirdness. No normal matter will do. Historians still argue whether Morris and Thorne truly believed their solution was a blueprint, or just a glorified thought experiment. But the math is tight. It's just expensive. Not in money, but in violations of common sense. One estimate says you'd need a shell of exotic matter with a density equivalent to negative Jupiter mass quantities surrounding a tunnel, perhaps only a few meters wide. And the moment you introduce a traveller or even a flashlight beam, you begin shifting the energy balances inside the tunnel. Unless you've pre-stabilized every centimetre with exotic support, it can collapse like a souffle in a thunderstorm. So of course, physicists got to work. What if, they asked, we could minimise the amount of exotic matter needed? And lo, the math adapted. Some models suggest you can thin out the exotic region, concentrate it just around the throat, use geometric tricks, or allow asymmetry to reduce the energy cost. Others propose cut and paste wormholes. Yes, that's the term. Where two regions of space are sewn together using what are called thin shells, boundaries between metrics, still theoretical, still wildly unstable, but mathematically clean. Let's also tiptoe into a terrifying branch of geometry called topology, the study of shapes and surfaces. You've probably heard the joke that a topologist can't tell the difference between a donut and a coffee cup because they both have one hole. That joke is disturbingly relevant here. Wormholes are essentially topological structures. You're taking the space-time manifold, the cosmic coffee cup, and folding, twisting, or connecting it in a way that breaks normal intuition. And these topological tricks are allowed, again, if the stress-energy tensor is weird enough. Fringe idea time. There's a line of thought that quantum gravity, once we figure it out, might allow wormholes to exist without exotic matter at all. That the geometry of space-time at very small scales could support non-trivial topologies by default. Think of it as space-time knitting itself into little loops and bridges, and then you just scale one up like inflating a bouncy castle made of gravity. And yes, the math gets worse, much worse. At some point you're dealing with Einstein-Rosen bridges, Kruskal extensions, traversable Lorentzian manifolds, and null geodesics that may or may not spiral into closed time-like curves. It becomes less about whether you can build a wormhole and more about whether the equations will tolerate your nonsense without throwing a tantrum. There are full doctoral theses written on whether certain wormhole metrics satisfy the flaring out condition, a geometrical requirement that keeps the tunnel from pinching off at the throat. It's the mathematical version of checking that your crawl space doesn't cave in while you're halfway through. And remember, all of this is assuming the classical equations still apply. We haven't even touched quantum field effects yet, which might destabilize everything via vacuum fluctuations, or semi-classical gravity, which combines general relativity with quantum expectations. Once you go down that path, you start needing something called the renormalized expectation value of the stress-energy tensor, which is as fun as it sounds. Yet despite all this, the math hasn't ruled them out. Not completely, not even close. There is no proof that wormholes are impossible, only that they are mathematically demanding, energy-intensive, and very, very particular about their surroundings. Kinda like your phone when it's looking for a signal in a concrete basement. So next time you hear someone casually drop the word wormhole, like it's just a zip file for space travel, remember the terrifying complexity behind it. Every wormhole solution is a carefully balanced monument of tensors, geometry, and outright stubbornness. You don't just draw a circle and call it a tunnel. You fight gravity, bend topology, summon negative energy, and pray the equations don't turn on you mid-transit. Still, the fact that math allows the possibility, that's enough to keep dreaming. You've wrangled tensors, tiptoed through time paradoxes, you've surfed black hole throats and felt your brain briefly melt under the pressure of exotic matter math. And now, here comes the real twist, the dimension behind the curtain. Because wormholes, for all their mystery, might not just be about space bending in our familiar four-dimensional universe. No, that would be too easy. Tonight, you take a step sideways into the idea that wormholes might only make full sense if we live in more than 4 dimensions. Let's unpack that, slowly, and with minimal existential whiplash. Right now, you live in what physicists call 3+1 dimensions. 3 of space, length, width, height, and 1 of time. That's the box your entire reality sits in. From breakfast burritos to black holes, everything you experience unfolds in those 4 woven threads. But here's the uncomfortable truth. The math doesn't care. The math says, sure, 4 is fine. But what if there were 5, or 10, or 11, and everything you see is just the shadow of a higher dimensional party you weren't invited to? This brings us to theories like Kaluza-Klein, string theory, and M theory, all of which suggest that the universe might contain extra spatial dimensions. They're just curled up, hidden, compactified, like little spatial noodles folded so tightly you can't move through them, at least not easily. And here's where wormholes re-enter the scene with a dramatic flourish. If you allow extra dimensions, the constraints on wormhole geometry start to loosen. You can cheat in ways that aren't allowed in just 4D spacetime. It's like playing chess on a 3-tiered board instead of a flat one. The moves get stranger, the possibilities wilder. In 5D, for example, spacetime can twist and link in ways that look impossible from your 4D perspective. A wormhole that seems to break causality in 4 dimensions might be perfectly stable and well-behaved when viewed from above, like a Mobius strip that only makes sense when you stop thinking in straight lines. Historians still argue whether the early proponents of extra-dimensional physics understood the wormhole implications. But one thing is clear. As soon as physicists started playing with extra dimensions, wormholes became more than curiosities. They became necessary artifacts, natural byproducts of a richer topology. One of the juiciest versions of this comes from brain world theories, like the Randall-Sundrum models. In these theories, your entire universe is a 3-brain, a three-dimensional surface floating in a higher dimensional bulk. Think of a soap film stretching across a multi-dimensional space. In that picture, wormholes might be projections of higher dimensional shortcuts. You see only the entrance and exit, like cave mouths on a hillside, while the actual tunnel runs through the bulk, hidden from 3D eyes. Even stranger, these higher dimensional wormholes might allow travel between separate brains. In other words, other universes, entire cosmoses, each with their own time, space, and laws of physics. Your wormhole might not just take you across the galaxy, it might drop you into an entirely new reality where gravity is sideways, or where cats are in charge and quantum mechanics is optional. Fringe idea time, because of course, some researchers have speculated that gravitational anomalies, like dark matter halos or sudden lensing effects in deep space, might be signs of higher dimensional mass leaking into our universe through wormholes. We can't see the bulk, but we feel its fingerprints, like shadows on the cave wall. And get this, the Large Hadron Collider has actually run simulations exploring the idea that particle collisions might briefly reveal tiny, higher dimensional wormholes, not stable or useful ones, but flashes, blips, transient distortions in the geometry of space-time. So far, nothing definitive, but the models keep getting updated. Another angle, string theory with its 10 or 11 dimensions depending on your flavour. Strings, the fundamental units of matter, vibrate in these extra dimensions, and certain configurations called D-branes might naturally allow connections between distant regions of the higher dimensional space. That means wormholes could be topological necessities, not speculative oddities. In that view, wormholes aren't bugs in the code, they're features. Let's pause here, take a breath. Because if your brain is curling into its own extra-dimensional pocket, that's normal. This stuff is not meant to be digestible in one sitting, unless you've got a math degree and a mild disregard for sanity. But let's look at it another way. You're in Flatland. You're a two-dimensional being, a square, perhaps. One day, a sphere passes through your plane. What do you see? Just a circle, appearing, growing, shrinking, vanishing. The third dimension remains invisible to you. Now flip that. You're a 3D being. What happens when a 4D object passes through your space? You see strange distortions, disconnected entrances and exits, geometry that feels impossible. Wormholes, maybe, aren't tunnels at all, but higher dimensional curves peeking into your lowly 3+1 world. A higher dimensional poke. Fringe theorists love to suggest that all of space-time, what we call the universe, might be just a slice of something vastly bigger. That wormholes are not exceptions, but samples of a geometry we barely understand. And if that's true, then the search for wormholes is also the search for what lies beyond our dimensions. Not just far away in space, but up, in a direction we don't even have words for. There's even a spooky symmetry to it all. The same equations that describe black holes in 4 dimensions have analogues in 5 dimensions. The same way you can roll a 2-dimensional surface into a cylinder, or twist it into a torus, the shape of the universe itself might be coiled in ways that naturally create shortcuts. If we could move freely through these extra dimensions, if we could build machines that don't just warp space but step out of it, then building a wormhole might be as simple as walking around a corner. But until then, we're stuck in 4D, watching shadows, feeling the pull of gravity like a finger dragging across a page, and wondering whether the universe is playing with dimensions we can't yet reach. Still, the math leaves the door open. And somewhere beyond that door, a tunnel might already be waiting. You've spent the night burrowing through the folds of reality, stitching points in space-time, flirting with extra dimensions, and entertaining the idea that wormholes might be hiding under the rug of our universe like clever cosmic misprints. But what if wormholes aren't just shortcuts across our universe? What if they're bridges to others? Yes, it's time. You knew it was coming. Buckle up. Or, continue relaxing under your blanket, because tonight we're opening the trapdoor beneath the very idea of reality and peeking into the shimmering abyss of the multiverse. And if wormholes can do what the math says they might be able to, they could be cross-dimensional highways, tunnels not just across space-time, but between fundamentally different universes. It's a lot. So let's start slow. You've probably heard of the multiverse, one of modern physics' most tantalizing, controversial, and meme-inspiring ideas. It comes in several flavors, like a theoretical Baskin-Robbins. The quantum multiverse, where every possible outcome of every quantum event splits off into a separate universe. The cosmological multiverse, where eternal inflation spawns countless bubble universes, each potentially with its own laws of physics. The string theory multiverse, where extra-dimensional landscapes yield trillions of possible vacuum states, each one a separate reality. And of course, the fan favourite, the parallel worlds idea, where there might be versions of you in slightly different outfits making slightly better decisions. So where do wormholes fit into this mess? Well, according to some interpretations of general relativity and string theory, a wormhole doesn't have to connect two locations in the same universe. It could, theoretically, link two entirely separate spacetimes. Not just Alpha Centauri and Earth, but our cosmos, and a totally different one with pink stars and sideways gravity. In fact, there's a class of solutions to Einstein's equations that allow for this. They're sometimes called inter-universe wormholes or trans-universal tunnels. Terrible name for a band, excellent name for a concept. Imagine a wormhole that begins in our universe and opens in a region where the vacuum energy, the particle types, even the number of dimensions are different. A place where the speed of light is slower, or where electromagnetic force doesn't exist, or where space itself curves in on itself after only a few kilometers. Historians still argue whether any of these wormhole multiverse connections could be stable. Most models say no, they'd collapse instantly due to differences in energy and structure between universes, like trying to glue together two jigsaw pieces from different puzzles. But the math keeps the window cracked open. One theory that tiptoes into this territory is eternal inflation. In that picture, our universe is just one bubble in an infinite foamy sea. Each bubble is a different universe, born from quantum fluctuations in the inflating vacuum. They're causally disconnected. No signals can travel between them, unless there's a tunnel, a wormhole, a bridge that formed during the inflationary phase and got stretched across the foamy divide. Could one of these bridges survive the chaotic birth of universes? It's deeply speculative, of course, but not prohibited. Some physicists have even wondered if primordial wormholes, tiny tunnels created in the Big Bang's first microseconds, might still exist, linking us to sibling universes. If one ever drifted close enough to Earth, we might see a strange gravitational signature, a sudden tug, a hole in the cosmic microwave background, a region of sky that doesn't quite add up. Fringe idea time. What if black holes in our universe are wormholes to other universes? This one's a fan favourite. The basic premise is that the matter falling into a black hole doesn't vanish or get destroyed. It gets funneled into a different universe entirely. A cosmic recycling system. Your socks don't disappear in the dryer. They just slip through a Schwarzschild bridge and emerge in a parallel dimension, slightly lintier than before. In this view, every black hole could be a seed for a new universe, or a mouth of a wormhole leading into another. The other side? Who knows? A fresh Big Bang, a mirror universe. A space where the laws are reversed and gravity makes things lighter the closer they get. Again, there's no evidence for this, just equations that don't entirely rule it out. And that's where wormholes shine best, in the hazy margin between the known and the maybe. The idea that space can be bent is already weird. The idea that it can be punctured, that it can open a door to a reality with different physics, is nothing short of terrifyingly beautiful. Of course, we're nowhere near testing this, but there are indirect hints. Some cosmologists have noted anomalies in the CMB, cosmic microwave background, that could, just maybe, be scars from early wormhole formation. Others have run simulations suggesting that certain types of gravitational lensing, light bending in just the wrong way, might point to the influence of a mouth not anchored to our universe. And what about the famous ER equals EPR conjecture? You remember that from earlier. It connects wormholes, Einstein-Rosen bridges, to quantum entanglement, EPR. One fringe interpretation says that if two particles are entangled, they may be linked via a microscopic wormhole. Stretch that idea, now apply it to universes. Could our universe be entangled with another one, connected not just in concept but through geometry? Imagine peering into a wormhole and seeing not another star or planet, but a sky that's wrong, a reality that runs on different rules, a glimpse of something profoundly foreign, and yet made from the same cosmic stuff as you. It's not all sunshine and multiversal picnics, though. Interuniversal travel via wormhole raises massive problems. Stability. Different vacuum energies might tear the tunnel apart. Causality. If time runs differently there, you risk paradoxes on an even more catastrophic scale. Contamination. Matter from one universe might be incompatible with the physics of another. You could collapse an entire world just by stepping through. Oops. But here's the kicker. If wormholes do allow multiverse travel, they would change our understanding of reality completely. Not just practically, but ontologically. You wouldn't just be travelling far, you'd be leaving the only framework you've ever known. Physics itself would become regional. And yet, the math still hums, quietly, persistently. Somewhere out there, or maybe right here, folded up small, waiting, might be a tunnel. And on the other side, not another planet, not another star, but another everything. You've walked through folded dimensions, you've tiptoed between brains, you've stared into the glittering mouth of a tunnel that might just open into another everything, and now, as you sit with the shiver of that idea still lingering in your chest, a sobering question arrives. Quiet, heavy, and inescapable. How much energy would it take to actually do this? Ah, yes, the cosmic price tag. Because wormholes, no matter how mathematically elegant, no matter how tantalizing in theory, aren't free. If you want to punch a hole in reality, bend it like origami and keep it from slamming shut like a bear trap made of spacetime, you're going to need fuel. And not just any fuel. We're talking about energy levels so absurd they make nuclear bombs look like flickering matchsticks. Let's pull back a moment and remember the basics. To keep a traversable wormhole open, you need to balance the intense inward pull of gravity at the throat with something pushing outward. That's your exotic matter, the negative energy density we've already played with. It doesn't just resist collapse, it actively pries the geometry apart, creating a throat wide enough for light, matter, or regrettably curious space tourists to pass through. But the amount you need? Yikes. According to Morris Thorne wormhole models, even a modestly sized tunnel, say, a couple of meters across, could require mass energy equivalent to the Sun. Yes, the Sun, not a chunk of it, the whole thing, but negative energy form, which again is something we don't even know how to produce in large quantities, let alone concentrate and contain like an obedient physics-defying foam. And that's just the starter pack. The energy requirements scale dramatically with the size of the wormhole and the stability time. Want to keep a throat open for a few seconds? Add more energy. Want to keep it open indefinitely? Get ready to drain entire galaxies. Some calculations estimate that sustaining a large human-safe wormhole for extended travel might require negative energy equal to the total mass energy of Jupiter or more. Even Kip Thorne, eternal optimist of theoretical wormholes, admitted that the required energies are formidable and would require quantum fields in states not yet achieved by any experiment. That's physics speak for good luck and don't hold your breath. Historians still argue whether these extreme numbers are due to our limited understanding of quantum gravity, or whether the universe is trying to gently warn us that wormholes are technically allowed, but practically forbidden. There are workarounds. Theorists have played with thin shell wormholes and asymmetric metrics that require less exotic matter. Some suggest that if you start with a pre-existing wormhole, say, one left over from the early universe, you could manipulate it with far less energy than starting from scratch. Think of it like remodeling an ancient stone tunnel instead of blasting one through a mountain. Fringe idea time. One proposal involves using cosmic strings, hypothetical, ultra-thin, ultra-dense filaments formed in the early universe. If two cosmic strings were brought near each other at high speed, they could, according to some models, create a stable wormhole-like structure. This might be far more efficient than exotic matter alone. Of course, we've never found a cosmic string, but if they exist, wormhole potential unlocked. Another oddball proposal, Casimir energy harvesting. You remember the Casimir effect, that spooky little quantum interaction between two plates in a vacuum. Some theorists suggest you could stack Casimir plates in a clever configuration, extract the negative energy, and concentrate it into a structure that mimics exotic matter behavior. Sounds promising, until you realize the effect is tiny. You'd need more plates than atoms in the known universe to generate even a fraction of the required energy. And yet some physicists persist. They argue that our assumptions about energy needs might be off, that once we understand quantum gravity, or discover a grand unified theory, the energy cost could drop dramatically. What looks impossible now might be achievable in a few centuries, or even sooner if we stumble across new physics. Still, even the dreamers admit the logistics are, shall we say, non-trivial. Let's pretend, just for a moment, that you had the required negative energy. You've stabilized the wormhole throat, anchored it with clever geometry, and lined it with quantum field trickery. Now comes the next problem: containment. Negative energy isn't just hard to find, it's unstable. Even in theory, fluctuations in quantum fields could destabilize your carefully crafted tunnel. One sudden spike in Hawking radiation, and your wormhole collapses, or worse, explodes in a burst of Planck-scale chaos. So you need energy control systems capable of manipulating space at a precision we don't even have words for yet. Forget switches and wires. Think field-shaping technology that can respond in real time to quantum-level distortions. Some researchers refer to this as metric engineering, a term that sounds like sci-fi but has real theoretical teeth. The idea is to design and control the geometry of space-time itself, as if it were a programmable medium. Light goes this way, mass goes that way, and the tunnel stays open. If we ever developed the tech to do that, wormhole travel wouldn't just be possible, it would be routine. But until then, we're left staring at the bill, and it's steep. This is the price of breaking cosmic distance, of shortcutting the stars, of holding open a tunnel that space itself desperately wants to collapse. Yet here's the strange beauty of it. The universe doesn't slam the door, it just says you can do this. But you better really, really want it. So maybe someday we'll find a workaround, a low energy shortcut, or maybe we'll discover that wormholes aren't built, they're found. Tiny cracks in the space-time wall ready to be widened. But for now, the cosmos waits, quiet, curled, and unbelievably expensive. You've run the numbers, grimaced at the energy costs, and realised that building a wormhole would require an energy bill you can't even imagine. Galaxy-sized, with absolutely no option for monthly instalments. So naturally the next question starts itching at your brain. What if we don't build one? What if we just find one? Maybe nature, in all its ancient weirdness, has already done the heavy lifting. Maybe the universe has been experimenting with space-time tunnels since the beginning, and one of them, just one, is still out there. But how would you even begin to detect a wormhole? Let's say you're an astronomer peering through a state-of-the-art telescope. The sky is silent, the stars behave. But hidden in that ocean of darkness, somewhere in the swirl of galaxies, might be a wormhole, grinning like a secret doorway you weren't meant to notice. And yes, there are ways we might spot one. Let's start with the obvious candidate, gravitational lensing. Einstein taught us that mass bends light. When a massive object sits between you and a more distant light source, it can warp the light from behind into arcs, rings, or multiple images. This is gravitational lensing, and we see it all the time with galaxies and black holes. But here's the twist. If a wormhole exists, especially a traversable one, its gravitational signature would be weird. Some models predict that a wormhole could produce non-standard lensing effects. Light might curve toward or away from it in unusual ways, depending on the type of exotic matter at the throat. You might see a shadow with no mass to account for it, or a star behind the wormhole might appear duplicated, distorted in a way that screams tunnel rather than black hole. Fringe idea alert. One theoretical paper suggested that a wormhole could create a central brightness, a kind of luminous ring with unexpected symmetry. The kind of structure that would confuse an astrophysicist just enough to say, what is that? Historians still argue whether any currently catalogued gravitational anomalies might already be wormholes. Some astrophysicists point to certain stars whose movements suggest invisible, massive objects, but that don't behave quite like black holes. Are they wormholes? Unlikely, but the door isn't locked. Now let's get more speculative. What if a wormhole had one mouth nearby? You wouldn't need to see both ends to detect it. The gravitational distortion from just one side could affect a local space. Planets might wobble, light might flicker strangely, particles might behave with subtle asymmetries, something physicists are already tracking in experiments. You might even see a disruption in cosmic background radiation, a faint cold spot in the sky, where microwave photons took a shortcut through the tunnel, arriving sooner or with different energy signatures. Some anomalies in the CMB have been spotted, though most are chalked up to instrumentation quirks or statistical noise. Still, maybe one is more. There's also the possibility of radiation leaks. If a wormhole connects two vastly different regions of space or time, there might be differences in ambient radiation. One mouth could act as a fountain, spewing out particles from somewhere else. It might even appear like a strange kind of cosmic ray source, pumping out high-energy particles that don't match the surrounding conditions. Or imagine this. You detect neutrinos, those ghostly, barely there particles, arriving from a location with no visible source. They pass through everything, so they could, in theory, be the perfect wormhole messengers. One researcher even proposed searching for neutrino echoes, identical particles arriving seconds apart, bent or redirected through warped space-time. Do we have the sensitivity to test this yet? Not really, but we're getting closer. Telescopes like the James Webb Space Telescope and Vera Rubin Observatory will give us more precise data on cosmic lensing, allowing us to spot anomalies we might have missed before, and instruments like LIGO and Virgo, designed to detect gravitational waves, might one day pick up non-standard waveforms. Ripples not from black hole collisions, but from something stranger. In fact, some theoretical models suggest that a wormhole merging with a black hole could release a gravitational wave with a unique signature, a kind of space-time chirp that doesn't match anything else we've seen. Some physicists are already combing through LIGO data, hoping for a whiff of something exotic. Another approach? Look for disappearing or appearing objects. If a stable wormhole had one mouth inside our galaxy, and the other in some distant region, objects might appear to vanish as they pass through. 1 second you're observing a faint dwarf star, the next it's gone. No explosion, no collapse, just missing. Or maybe you detect an object that wasn't there yesterday, suddenly burning in a patch of sky you've scanned 1,000 times. Of course, you'd need long-term, high-precision sky monitoring to catch something like that. But hey, we're doing that already. And as AI begins helping us process these massive data sets, we might start noticing patterns we missed before. Fringe theory time again. Some propose that fast radio bursts, those mysterious millisecond-long flashes from deep space, might be signals from wormhole mouths. Not from aliens dialing in a message, but from objects or energy passing through tunnels, briefly disrupting local space-time in detectable ways. Are FRBs actually wormhole burps? Probably not. But it's not the worst idea ever proposed at 3 AM. by someone sleep-deprived and standing too close to a whiteboard. The truth is, detecting a wormhole would likely require multiple lines of evidence: gravitational distortions, unexplained radiation patterns, maybe even particle trails that hint at non-Euclidean pathways. But once spotted, it would be the greatest scientific discovery in human history. It wouldn't just confirm wormholes exist. It would mean the universe is navigable in ways we never imagined, that light years are optional, that barriers are invitations. And here's the best part: we wouldn't have to go looking far. Because if wormholes are out there, especially the naturally formed ones, somewhere in the web of dark matter between stars, maybe coiled in orbit around a rogue planet, they might already be close. So close that the next big astronomical glitch might not be a glitch at all. It might be a door. So, let's say you found one. A wormhole, real and yawning in the darkness, its mouth quietly rippling against the fabric of space like a wound that never closes. It's stable, it's reachable, it's whispering sweet equations to your most optimistic physicists. Now comes the question no one really wants to answer, but everyone must. What could go horribly, terribly wrong? Because let's be clear, using a wormhole isn't like booking a flight to Mars. It's not even like launching yourself into a black hole and hoping for the best. A wormhole is a shortcut through the rules, and shortcuts have a way of skipping over the warning signs too. So tonight, we're staring into the abyss with eyes wide open, compiling a list of the most unnerving and occasionally hilarious ways a wormhole could go sideways. First, the classic collapse. Even in the most optimistic models, a wormhole is constantly teetering on the edge of gravitational self-destruction. You add too much mass, let in a bit too much radiation, or let a passing neutrino wink at it the wrong way, and the whole thing might pinch shut mid-transit. Best case, you're spat back out the way you came. Worst case, you're crushed into Planck-scale linguine and ejected into a baby singularity that forms at the throat. It's like a trapdoor, except the floor is also on fire, and the fire is made of quantum foam. Next up, radiation. Because even if the wormhole stays open, it might not be a quiet, cozy tunnel. Some models predict intense radiation fields near the throat, not just light, but X-rays, gamma rays, particle storms dense enough to fry electronics and make your spaceship glow in the dark for centuries. One particularly cheery idea suggests that the exotic matter lining the throat could become unstable, generating a kind of feedback loop that floods the interior with high-energy particles. Imagine stepping into a gentle hallway and being immediately pelted with invisible bullets travelling near light speed. Fun. And then there's the sleeper threat. Time offset errors. Remember, wormholes can connect different points in time as well as space. That's great. Until someone forgets to carry the one and accidentally sets the destination to 500 years ago. Now you've emerged into a timeline that hasn't yet invented antibiotics, and the locals are very suspicious of your glowing boots and metal pants. Worse, your return trip may not be possible. Some wormhole models only work one way if the mouths aren't synchronized. Historians still argue whether one-way wormholes would be usable at all. But if you step through and the geometry shifts even slightly, you might never be able to reopen the path. Or worse, the path opens for something else. Because yes, we've arrived at the most sci-fi and arguably most legitimate concern, accidentally weaponizing space-time. See, wormholes aren't just shortcuts, they're tools. If you can stabilize and control one, you might not stop at travel. You might start using wormholes to deliver energy, to bend light paths, to aim causality. In one speculative nightmare, a wormhole mouth is placed near a star, perhaps in orbit around a black hole, and its output end-aimed somewhere else. You've just created the ultimate gravitational cannon. Want to send a radiation burst across the galaxy? Just aim your wormhole mouth toward your target and let the local star do the rest. In another scenario, someone uses a wormhole to send objects back in time and change history. Even if paradoxes are avoided through multiverse splitting or self-consistent loops, the outcome is unpredictable. You might wake up in a universe where you never existed. or where someone else invented wormholes first and used them better. Fringe idea time. Some theories suggest wormholes could destabilize vacuum states. If our universe exists in a false vacuum, essentially a metastable state, then a violent event like a wormhole collapse could trigger a transition to a lower energy state. That means total universe reset. Don't worry, you wouldn't notice. It would happen faster than light could warn you. Then there's the issue of biological stability. Let's say you step through a wormhole and everything's fine physically. You arrive intact, no radiation, no collapse. But the passage itself might alter molecular structures. Some models suggest changes in inertial frames inside the tunnel could shift how particles interact. Translation. You could come out a little scrambled, cells might mutate. Quantum decoherence could wreak havoc on your memory. Time dilation could desynchronize biological rhythms. There's even the disturbing idea that your consciousness could drift out of phase with your body if the space-time flow isn't perfectly smooth. You'd still be you, just weird. Off. Wrong in ways only noticeable after it's too late. And let's not forget the very real risk of causality infection. In physics, causality is sacred. It keeps events in order, gives meaning to before and after. But wormholes let you loop. They let information arrive before it's sent. If you send a message through a wormhole into the past, and that message prevents itself from being sent, congratulations, you've just created a logical paradox. What happens then? One view says the universe prevents the paradox. Self-consistency always wins. Another says the timeline splits, multiverse branching. But there's a darker third option. The entire causal structure of the wormhole region becomes unstable. Events ripple out of order. Effect precedes cause. History loops and folds into nonsense. In short, your wormhole might turn the laws of physics into spaghetti. So, could it work? Yes. Could it kill you in 17 different ways before lunch? Also, yes. That's the curse of wormholes. They're not just marvels. They're edge cases. They exist at the border between possible and forbidden, nestled in the cracks where the universe mutters, "Fine, but only if you don't mess it up." And guess what? We're the species that always messes it up. Still, we dream, we plan, we build simulations and scribble notes on napkins at 3 a.m, because the risks, however terrifying, are also a kind of proof that wormholes matter, that they touch something deep, some primal part of us that longs to connect, to leap, to understand what lies just beyond the veil. And maybe one day, when we're wiser or bolder or desperate enough, we'll step through. And if it all goes wrong, well, at least you'll have the best view in the universe on the way out. So here you are, stretched across the cosmos in thought, having journeyed through the science, the math, the maybes, and the mildly horrifying possibilities of collapse, radiation, and cosmic spaghetti. And yet, after all that, the question still lingers. Why do wormholes matter? Not just to physicists scribbling on blackboards, or sci-fi writers crafting their next warp jump twist. Not just to engineers dreaming of warp cores, or conspiracy theorists mapping suspicious gravitational anomalies, but to you, to us, to the very way we think about our place in the universe. Let's rewind for a moment. At the beginning of this journey, we imagined space as a vast, unyielding void, cold, distant, governed by the harsh realities of light speed and interstellar loneliness. You learned that even the closest stars are so far away they might as well be myths. That space doesn't just separate, it isolates. But then wormholes arrived, and with them came possibility. Because wormholes break more than distance, they fracture assumption. The assumption that there's only one way to get from A to B. The assumption that time moves in a straight line. That the speed of light is a wall rather than a suggestion. That the universe has to play fair. Wormholes, even in their most theoretical form, are hopeful rebellion. They whisper, what if there's another way? That's why they matter, even if we never build one. Even if the energy costs are impossible and exotic matter remains as elusive as a polite YouTube comment section. even if every natural wormhole out there is the size of a quark and collapses before we can blink at it, wormholes still matter because they stretch the edges of what we allow ourselves to imagine. Historians still argue whether the earliest mentions of wormhole-like concepts in ancient myth, portals between worlds, hidden doorways in the sky, were dreams, metaphors, or some ancient intuitive grasp at cosmic truth. But in every era, we've tried to reach beyond. Whether through magic or machinery, we've looked at distance and asked, what if I could skip it? And wormholes are science's most elegant, most dangerous answer to that question. They also remind us that the universe is not static, that reality itself has layers, depth, curvature, texture, that the same space-time that carries your steps down the street could also, in the right conditions, loop back on itself and let you walk out of yesterday. They matter because they make time bendable, because they make the impossible feel technical. You've seen now how wormholes are not simple cracks in space. They're geometric expressions of energy and curvature. They require negative mass, fine-tuned metrics, control of space-time on a level we've barely begun to understand. And yet, the math allows them. Every scientist knows that feeling. The moment when a solution pops out of a blackboard like a hidden door, not because you forced it, but because it was always there, waiting. Wormholes are like that. Uninvited, improbable, and quietly persistent. And here's something else. They don't care about your technology. They don't care about what century you live in. They are ideas baked into the structure of the universe. Whether we build one or not, the mere possibility means we have to rethink what we thought was true. That alone makes them sacred. Wormholes matter because they represent the kind of mystery that invites action. Not passive wonder, but curiosity with teeth. The kind that makes you ask how, not just what if. And maybe they matter most because they remind us we're not done. Not done exploring, not done questioning, not done trying to outwit the walls the universe puts in our path. Because we're a strange species. We invent mathematics that breaks our own brains. We launch telescopes just to stare deeper into the dark. We dream of faster-than-light travel when we can barely leave our own planet's gravity well. And we believe, deep down, that somehow, someday, the shortcut will open. So we keep building models, we keep listening to the sky, we keep asking absurd questions at 2 a.m. while the rest of the world sleeps. Because if even one wormhole exists, if even one can exist, then the universe isn't just big, it's connected. And maybe, just maybe, we are too. And now, the math has quieted. The tunnels have faded back into the dark. You're still here, body wrapped in blankets, thoughts still circling like slow satellites. But the wild spinning of space and time has eased into a hush. You've wandered through the impossible tonight, not just across galaxies, but between dimensions, between ideas. You've peeked into the mouths of theoretical beasts and stared down tunnels carved into the spine of reality. You've watched the universe fold and unfold like paper, whispering secrets through equations older than stars. And somehow you made it through. You imagined matter that falls upward. You weighed the energy of entire stars just to hold a doorway open. You chased light through tunnels that don't follow lines. You dared to question causality itself, to ask, with sleepy eyes and a steady breath, what if time could bend? It's a strange comfort, isn't it? That the universe is still full of mysteries it hasn't yet closed off. That beyond the walls of what we can touch and measure, there's still room for wonder, for quiet rebellion, for dreams made of tensors and tunnels. Maybe wormholes will always live in theory, written in chalk, blinking through simulations, folded into bedtime thoughts like this one. But maybe not. Maybe the next whisper from the cosmos won't just be a star. Maybe it will be a signature, a subtle curve of light, a sudden vanishing, a doorway left open a little too long. And maybe one day we'll step through, but not now. For now, the equations can rest, the stars can keep their secrets, and you, clever, curious, cosmic you, can drift slowly towards sleep, knowing that space itself might hold you and fold you across the sky. Sweet dreams.